That's a good threshold. Okay. Good morning, everyone, and good evening to Karl. Today, we are honored to have Dr. Karl Gordon from the Space Science Institute as our colloquium speaker at ASIAA. Karl got his PhD from the University of Toledo in 1997 on interstellar dust research. After that, he became a postdoc at Louisiana State University. Then he worked at the Spitzer MIPS team at the University of Arizona for 10 years. Karl joined STScI in 2007, and he is also a guest professor at the University of Ghent since 2011. Karl has been investigating the properties of interstellar dust from various methods, including dust emission, extinction, and modeling. And he also works on supporting JWST, as you might have noticed in some of the JWST newsletters or broadcasts earlier this year. Personally, Karl's studies of dust in the measuring clouds in the Heritage Project marked the beginning of my own research of dust. I also benefit a lot from his dust BFF fitting method, which is widely used in the projects I participate in. So without further ado, please join me in welcoming Karl.
Yep. Thanks all. All right, well, thank you very much for giving me this opportunity to talk about dust with you. It's one of my favorite topics, and I always like a captive audience. So hopefully you won't run away. So I'm going to talk about dust extinction in the diffuse interstellar medium, which doesn't always have pretty pictures, but fortunately JWST released this very amazing picture to me of the pillars of creation just a day or two ago. So I can at least put that on my main front slide. Okay, so let's see if it goes. There we go. So I'm going to tell you where I'm going to go. Here's the summary of what I'm going to tell you about, and then we'll go through it all, and you can see whether or not I actually made it to my summary. I actually convinced you of all the things. So I'm going to tell extinction measurements are fundamental to our understanding of dust. And so what I'm going to tell you about is a lot of spectroscopic extinction measurements from the far ultraviolet to the mid-infrared in the Milky Way, work that we've been doing recently, and what we found. I mean, overall, it's quite smooth. The extinction is pretty smooth. There's a few broad features, and there's some new ones that I want to draw your attention to. There's an intriguing correlation, and there's some comforting non-correlations. And then the most recent work I'm doing right now in the Milky Way is one RV extinction relationship for all wavelengths. Hopefully useful for all, including us dust people. I'll talk a bit about beyond the Milky Way. What do we know about extinction beyond the Milky Way? And in general, it's mostly like the Milky Way, but not all. And the not all is an important part of the discussion. I'll talk a little bit about the future work we're hoping to do or are planning on doing with Hubble and JWST. And really, it's like anything. It's more galaxies, more environments, and larger samples. All right, so that's where I'm going to go. So let's see if we can get there. So extinction, it really gives us critical clues to dust grain abundance, size, composition, and shape. And really, these clues are both in the continuum and the features. And one of the nice things about it is a very straightforward measurement. I'm going to focus on spectroscopic measurements because I want the features and the continuum. And as always with any of my talks, it's biased by my views and my knowledge. And so it's not comprehensive. And so I'm hoping if you have any questions, feel free to ask me. There's a lot of things about dust I'm not going to cover because I only have 45 minutes. I'm not going to talk about dust scattering, right, or dust emission, the atomic composition of dust, dust polarization, or dust grain models. These are all extremely important, but they're just not the focus of this talk. I do want to point out that I'm going to talk about dust extinction and not attenuation. And it may be that these things seem the same thing, but there are some significant differences that we should be aware of. So extinction, by that I mean this simple graphic here, which is there's a star and there's a bunch of dust in front of it that's not really near the star. And what we have is the dust absorbs and scatters the photons out of the line of sight. And it's very specific to this geometry of point source dust. Now, point source with dust. And the nice thing about when we measure the extinction, it's proportional to the dust grain properties alone, the amount of dust, the composition, etc. Whereas attenuation, this is kind of what we see in galaxies. This is where our beam is big and we have multiple stars and clouds of dust, and things are a bit more, the geometry is a bit more complicated. And we have both scattering into the line of sight and not just out, as well as varying extinction to the stars. So these are two radiative transfer effects that make it more challenging to interpret an attenuation curve. And so it's harder to get to the exact dust grain properties. So I'm going to focus just on extinction because it's simple. And one thing I'm learning as I become more senior is I like simpler things than more complex things. And just to illustrate the difference here, one of the major differences is on the top, I'm showing extinction curves, in absolute extinction curves for 3 different columns of dust, parameterized by AV of 1/2, 1.5, and 2.5. And then if you normalize those total extinctions by their extinction at AV, the shapes all line up. There's the same shape. So that's easy. That's nice. We can compare things at different columns. But when we go to attenuation, this is a very, very simple geometry. Now, if I have differing amounts of optical depth, again, the curves are different in the absolute term. But when I normalize them to V-band, the shapes don't all agree. So we actually see shape variation, even though the same kind of dust is in these systems. But because we have these mixing effects and radiative transfer effects, the shape changes. And that makes it more complex. So when I say it's straightforward, I mean, it's basically a division, and that's the simplest thing. And so how do you measure an extinction curve practically? You basically measure a star that you think has dust in it. That's the red curve here on the top as a function of wavelength. And then you measure another one that's that's almost exactly the same star. So it's a star that has the same spectral type and the same metallicity and the same luminosity. So you know that it's basically the same physics. One has dust, one doesn't. You divide. And I'll show you a little more in a second, but then you get an extinction curve out of that. In general, we like to observe OB stars because they're luminous at all wavelengths and they have fairly simple atmospheres. So sometimes we don't even need to observe the unreddened version. We can just use a stellar atmosphere as a model. And by luminous at all wavelengths, I mean from the UV to the mid-infrared. These are some of the most luminous stars that are out there. So they're really nice targets. They're rare, so that's one drawback. So here's a few equations, but they're hopefully simple. So the idea is the basic measurement we make to measure extinction is a color excess, right? So basically, the excess color due to dust as a function of wavelength. The equations are here. It really boils down to we are just taking the log of the ratio of the reddened and comparison star at one wavelength and differencing it from the log of that ratio at another wavelength. The reason why we have to do this relative to a particular wavelength is because we don't know the distances to the stars accurately enough to get their intrinsic luminosities. And, you know, Gaia is awesome, but it's still not good enough. In general, it gives us this color excess, but we want to normalize to some dust column so that we can compare things at different dust columns. And there's various, EB minus V is one. I like AV because it's an absolute. And this just shows you how, if you have AV, how you can actually transform E lambda minus V to AV, to A lambda over AV, excuse me. Divide by it and add 1. It's pretty easy. And we usually determine AV by extrapolating the extinction curve to infinite wavelength. And why do we do that? Because at infinite wavelength, the extinction has to go to 0. And what we've already found out is the dust grains are small enough that by the time we get out in the near infrared at a couple of microns or even longer, we're near where the extinction is very, very low. And so by the extrapolation is not a big extrapolation. And I show here one of the ways we do it is you basically multiply E K minus V by 1.1. It's 1.12, whatever, something like that. It's like 10%. We're within 10% of the answer once we get the K band. So it's straightforward to do. There's always subtleties to all this, but in general, it's pretty straightforward. As I said, I like straightforward. I started off as a grad student doing dust rate of transfer. That is not straightforward. I guarantee you that. This is great. This is nice and simple. So one of the things I'm going to talk a lot about, and you may have heard about, is RV, right? We use RV as a shorthand for information about dust grains. And really RV is this total to selective extinction. It's just AV over EB minus V. So AV is a measurement of the total dust column, and EB minus V is the difference in extinction between those two wavelengths. Why? And we say that's on metric for the average grain size. Why is that? Really, it is that if you think about it, if you have very small grains, they're going to be efficient at shorter wavelengths of extinguishing the dust than at longer wavelengths. And so you can imagine in this case, more blue would be absorbed. So your extinction at B would be much larger than your extinction at V. So for whatever column, you're going to be dividing by a reasonable number, nothing too small. But then if you had very large grains, i.e. RVs large, now, it's a brick, right? So it extinguishes equally at B and V. So now you might imagine your EB minus V is very small. And so when you divide by it, your RV goes very large. And so that's why we have this idea that really small RV means smaller grains on average, and large RV is larger grains on average. And we're going to use that a lot. So I wanted to make sure I explained that hopefully well enough. Of course, if you have any questions, you can interrupt me or ask later. If we were in the room, it would be easier. I could see whether you were confused or nodding off, and change as appropriate. All right. So the other thing, in looking at dust extinction curves across a broad wavelength range, what we'll see in the literature is that there are two different wavelength scales. Wavelength we plot against the wavelength things. One is, which is kind of newer, is we plot it versus wavelength, usually log wavelength, because we're going over quite a large range. But for a lot of the original work, a lot of the work for many years, it's plotted as 1 over lambda, inverse wavelength. This is done the way, 1 over lambda, the wavelength scale is proportional to energy. That sounds awesome. And it emphasizes UV wavelengths, which I think is the real reason it was done, because there was a lot of UV work, and it makes the UV look big. And this is illustrated with the colors. So I've color-coded the wavelength ranges for UV, optical, near-infrared, and mid-infrared. And I'm going to use that throughout the talk because it does get confusing to have things flip back and forth. So hopefully it helps. Okay. Also, I'm mainly going to talk about diffuse dust and not dense dust. So diffuse sightlines, why am I doing it? There's a very practical region. That's where we have most of our information. That's actually where we have where most of our information about dust grains is from. All our dust grain models are based on diffuse dust. And so most of the studies are there. And these have AV values generally less than a few. And they don't, one of the tracers we use is this water ice feature at 3 microns, which I show an example there on the right. And we don't want them to have water ice. Water ice is an environmental tracer that tells us we're in a colder region that's probably shielded from the diffuse, from the radiation field, and we have significant accretion of gas phase material onto the dust grains. That's going to change their properties. I'm really excited about studying that kind of dust, the dense sightlines, but they're more challenging. They're higher AVs, and generally we only can get them in the near and mid-infrared, and there's more information. I want the full wavelength range, at least right now. All right, so let's talk about our galaxy for a little bit. It's kind of, there was significant amount of work in the optical, looking at the optical extinction curve. The optical extinction curve wasn't that exciting. It basically was linear with 1 over lambda with some wiggles. We're going to talk about those wiggles in a little bit. Those wiggles are interesting, and we've learned more about them. But they really kind of, the UV has dominated our study of dust for a long time, because when we finally got the first UV spectroscopy of hot stars, and this is the second paper showing a bump, because Ted Stecker did an earlier paper. This one just looks nicer. And this is from a rocket that he built and launched. Look, this is a single author paper. I want you to imagine being able to write that abstract. That is the abstract of the paper in 2 sentences. I love it. And now he was able to do this pair method and show very clearly, here's a UV extinction curve, and it looks like all the UV extinction curves, almost all of them we've measured since then. Notice I've got the purple and the blue to hopefully give you a guide where UV and optical are. All right. Then enter, and there's another reason UV dominated for so long, the International Ultraviolet Explorer was a satellite that was launched. It was put into geosynchronous orbit, And one of the amazing things about this is it had a very few observing modes. They were all spectroscopic. And so it has a very homogeneous data set with a large number of spectra all the same. It was also probably the last space-based observatory where you got to go observe, sit at this console at Goddard Space Flight Center or in Villanova in Spain. And you see the joystick. That meant you were joysticking the observatory to put your star in the slit. And so those days are gone. You can actually go to the Smithsonian Museum in Washington, D.C. and see that console that people used, which is, awesome from a history point of view. Okay, so IUE took lots of spectra, and there was just a explosion of extinction curves measured from these spectra. Many extinction curves, many papers. One of the kind of to summarize where we were at that point in the early 80s, lots of extinction curves. They look very nice. Their average is shown in all of those, and you can see there are ones that are below the average, they're above the average, they have weaker bumps, stronger bumps. And for a while, these were called, if they didn't agree with the average, they were called anomalous extinction curves. Turns out they're not that anomalous, and we'll see why in just a second. But that was kind of where we were. So then Ed Fitzpatrick and Dirk Massa started working on this, and they're kind of one of the two sets that really made real headway in our understanding of UV extinction. One is, so they were able to have an analytic model for the 2175 angstrom bump. They were the ones who introduced the Drude profile to explain it. And it fits very well. And that means we can now look at the central wavelength and the width of the bump, among other things. And the kind of amazing result here is the width varies over a large range, but the center wavelength does not. That's actually still very much a challenge for dust grain models to actually explain, because in general, we use a size distribution of small grains to explain the bump of graphite, and we don't understand why, and the size distribution has to remain quite narrow, and we don't really understand why how it can remain that narrow. So that's one of those clues of what dust is that's very intriguing, but we don't always have all the answers. The second thing that Ed and Dirk did, Fitzpatrick and Massa, was to look at the far UV rise. So they were able to look at this there was a curvature in the far UV as it goes up, right? This far UV has a strong slope, but then there's some curvature. And they were able to show that basically it has the same shape. And it's this simple cubic term. We'll talk about maybe why it's that way in a second. But they were able to parameterize it. So now you can measure the strength of this curvature with one parameter. And so they put it all together. And so now for the UV, they came up with a very simple model with 6 parameters, and that's it to explain the UV extinction curve. And that's shown here in these equations. The 2175 angstrom bump is the strength plus the width plus the center. There's a linear term underneath everything with a slope and an intercept, and the far UV rise is C4. Awesome. We now can distill these extinction curves down to 6 numbers. That gets us places. At about the same time, there was another realization that came out by Karl, Clayton, and Mathis in 1989, which is that if they plotted the extinction curves in A lambda over AV at a particular wavelength, and they plotted it versus RV, right? This is in fact, RV to the -1, so the selective to total extinction instead of the total to selective. It was pretty linear. It correlated quite strongly. And in fact, I think the amazing thing here is not only did it correlate at one wavelength, it correlated at many wavelengths in the UV and optical, which said that there are shape evolutions in the extinction curve, but the grains that are responsible in the ultraviolet, which are small, somehow react the same way as the grains in the optical, which are larger, right? There's correlated changes in the size distribution of the dust grains that mean the extinction curves vary together, the shape varies. And so they were able to derive this as the origin of the RV dependent relationships that say, give me an RV and I can give you a pretty good estimate of what the extinction curve for that sightline looks like. Now, I want to point out this just tells us how the average varies as a function of RV. There are clear deviations, and there'll be many more when we get out of our galaxy. And the deviations were known even all the way back when they first started off, right? So it's not a completely predictive way of doing it, but it does give you the average. This has been, more recent work has shown that, instead of using the Karl, Clayton, and Mathis did a few tens of sight lines, Lynn Valencic, for her PhD thesis, did 400 plus sight lines, all you can possibly, most of what you can do out of the IUE sample. She found an RV dependent relationship that was similar, but not quite the same as others that have been done previously. I think she also found deviations, as had been done previously, and that's shown in the lower right plot, where the delta is the deviation from, at that inverse wavelength, from the RV dependent relationship. And there's some very famous stars there. Now, I know all those star names now. When I was a PhD student, I didn't, but now I do. They're all familiar. And then, but the really thing I want to show is this top plot on the right, which shows you the distribution of the extinction stars in our that were used in this study. And this is kind of all we've got. So this tells you that really when we're talking about our knowledge of dust extinction, in general, we're talking about our knowledge within a 1 or 2 kiloparsecs of us. And that's it. So does that apply for the whole galaxy? We don't actually know. But that's a question maybe we can answer once we get out of the galaxy. All right, so that's kind of where we were with IUE. Awesome, lots and lots of stuff. Now, how about, let's go to a shorter wavelength. So IUE went down to about 1150 angstroms, but we can measure down to 912 angstroms. Of course, below 912 angstroms, we can't measure anymore. Well, we can measure, there are just no photons, because greedy hydrogen takes them all to ionize. So there's so much hydrogen that there's nothing below 912 angstroms for us from stars in the Milky Way. Except for 2, those are special cases in the local bubble. Don't worry about those. So fuse went up. This is another kind of similar to IUE in a sense that it took spectra only. It took them in a homogeneous way from a little below 912 angstroms up to 1195. Okay, we got a good overlap. So we can use these to study extinction below kind of 1150. Well, okay, there's a little more work needing to be done here. So in the middle plot here, these are spectra of fairly unreddened stars, but you can see there's a 2175 angstrom bump, but then when you get down into the fuse wavelength range, there's all these strong lines. They're not due to dust, they're due to molecular hydrogen, which has all these absorptions in below 1150. So one of the parts of this is we had to determine the column densities in the different states of molecular hydrogen and model it so we could actually take it out. And that's what's shown after we've taken it out, is in the bottom set of plots. So that was a complication. It took longer to get it done, but we got it done. And here's a set of 75 sight lines that also had IUE observations. So we have now the full UV extinction curve from about 3000 angstroms down to 912. Awesome. Well, at some level, the results were kind of boring. It's smooth. It looks like a fairly clean extrapolation of kind of the curvature we saw before. So on the upper plot here, I'm showing you the average a couple of different ways. But it kind of just keeps going up. And that was somewhat expected if our understanding of dust grains was right. And so what I'm showing here is a couple of models. And you notice there's a very strong feature at 14 inverse microns, or 800 angstroms for those of us thinking in angstrom space. And this is thought to be a second resonance feature from graphite grains. That's kind of how it was modeled. And to all intents and purposes, it's there. That's what we expect. That's what we expect. That's what we found. So we confirm that idea as best we can. Now, the other thing we looked at was residuals. It turns out, right, so we do this very simple 6-parameter fit from the Fitzpatrick and Massa 1990, subtract it, and that's in the bottom plot. There are some residuals. There's some things that are bigger than not, right? There's a couple in the blue region, which is where the blue points, which is IUE. There's a few in the green, which is fused. But those are actually, unfortunately, at places we know are due to stellar issues. The 2 lines in the UV and the IUE range are wind lines from these massive stars, which do not cancel out well. The winds are kind of unique to every star. And in the fused wavelength range, there are places where we say have Lyman alpha or Lyman beta, or a hydrogen absorption line. So again, very smooth. We didn't see any extra features to find. So there you go. All right. So more recently, Dries van der Putte, a postdoc who's working with me here at the Institute, studied now the combination of the UV extinction curves that we now have for these 75 sightlines and the H2 column densities that we have, which are fairly unique. I mean, it's challenging to get molecular hydrogen column densities. You need fuse. You need something in the far UV to get that wavelength range where you have all the absorptions. So now for the first time, we have a whole bunch of H2 column densities, and we have UV extinction curves. That's interesting because the reason, one of the ideas on how you form molecular hydrogen is you form it on, not one of the ideas, the way we form molecular hydrogen is we form it on dust grains, but molecular hydrogen can't survive in the general radiation field of the galaxy because it's got too much energy, it dissociates. So it probably needs to be shielded. So we were curious to investigate this. So Dries looked at a bunch of correlations, and there's a bunch I've kind of whited out. But the two I want you to look at is, as before, we found that the total column density, NH, is well correlated with the total column density of dust, AV. Great. That means that confirms what we all say, that the gas and dust is well mixed. You can see the other correlations don't work as well. You know, the atomic alone doesn't correlate as well as the atomic plus molecular. That's this plot. And you can look around at those. And the other one that was quite intriguing to us was this one down here in the lower right, which shows that the molecular hydrogen column density correlates quite well with the extinction at 1,000 angstroms. And the idea, the reason we wanted to look at that was the shielding idea. What, you know, is it shielding it? Things are forming there, etc. And so that was awesome. And we submitted the paper. And then the referee came back with a question. Oh, there's a hand up. Should I answer?
So why is NH? So, but what is a unit? Is it to? I'd like to know the units for. So for NH, it's to what is the unit for this column density? Because it's
so I'm not quite sure. I mean, you know.
Yeah, 2 times. I'm not sure if it's column density, yes. Right? Why this? Yeah.
Right. So you have column densities here. Right. We have the atomic hydrogen from fitting the Lyman alpha profile with the IUE data, and you have the molecular hydrogen from fitting all those lines and fuse. And so if you can add them together to get the total column density, right? The column density of atomics plus 2 times the column density of H2. Right?
Okay. So two times.
Yeah.
Two.
So these the two bottom, the bottom and middle row give you, that's the column densities that you measure from those 2 different components, and then you can add them together and get the total. Awesome, right?
Okay.
It's not complicated. Yeah. Simple. I like simple. So that's
sorry. It's something like 4 times 10 to 21 or something. Yeah, it's too small.
10 to the 21 here.
21.
Yeah,
okay.
10 to the 21.
I didn't
10 to the 21. 8 times 10 to the 21.
Okay.
Yeah, it's the Python way of adding it.
Yeah, thank you very much.
Okay. No worries. My pleasure. And so this bottom plot was very intriguing. It correlates well, and it goes to an A of 1,000 of about 3. We're like, oh, that's interesting. Submitted the paper. The referee asked us, well, could you go into that a little more? This is one of those cases where the referee is the one who really helps. And so Dries said, okay, what I'm going to do is I'm going to decompose A1000 into what's from the far UV rise, the C4, and what's underneath it. And amazingly, at that point, we found out that, in fact, the H2 column density is much better correlated with just the component that's due to this curvature in the extinction curve, that blue piece here, than the total. And in fact, not only that, but it's a much better correlation. I wish all my plots looked like this, just the blue points, but it goes through 0. So it says that when you have no far UV curvature, you have no molecular hydrogen, or vice versa. So for me, what this really says is the grains responsible for the far UV rise and the H2 are co-spatial. But this isn't the case for the 2175 angstrom bump, where in fact the correlation gets a little worse if you do this decomposition between, you know, C3 and the linear term underneath. So this is also telling us that the bump and the rise are not really from the same thing, which we did know because we already knew that C4 and C3 weren't well correlated. But this also enhances that statement and says they really aren't, and in fact they're probably not even co-spatial. Okay, so that's the intriguing correlation, right? That for the first time, we now have a component of dust that is correlated very well with just molecular hydrogen. And that's a new result that is still, it's in press, right? It will come out, it's on AstroPH, but and what that means is I think we're still trying to digest. Okay. All right, let's move on to the Hubble Space Telescope. All right, Hubble actually can go from 912 angstroms out to 2.5 microns, but really FUSE and IUE have really pretty much covered everything we needed in the UV range, except for a few sight lines, which we've done, but in the Milky Way, but not many. But where Hubble really came in is maybe in a place that's a little less expected, which is the optical. So we were able to get a whole bunch of spectra of optical, of the same extinction curve stars, right? Same ones where we have IUE. But now we can get optical spectra from space and not from the ground. So we had much better we get great absolute flux calibration, and we didn't have the atmosphere that was interfering with us, especially in the red, where there are starting to be significant atmospheric absorption. So here's a few of the extinction curves that we studied on the right, and these are showing this is the actual extinction curve for just the optical region. That's why it's mainly blue on the wavelength scale. And it's versus 1 over wavelengths, and it's kind of linear, except if you look at it, they're kind of wiggling around. They're not actually perfect lines at all. Now, there are some stellar mismatches. That's in the green little things at the top showing H alpha and helium. And there's some both interstellar lines, calcium and sodium here, as well as the diffuse interstellar bands. I'm not talking about the diffuse interstellar bands. I have some concern that they're not really dust, they're more molecular. So, but that's a separate topic. But really what I'm talking about is these wiggles here. You can actually see things wiggle. All right, that's what's called and has been called for decades very broad structure. And very broad structure was simply you fit a line to these data and subtract it, and whatever was wiggles were called very broad structure. Maybe not the most useful definition, but interesting. So from this data, Ed was able to go ahead and derive a RV-dependent extinction curve relationship now that's at spectroscopic resolution in the optical and in the UV, whereas before we would have been doing this spectroscopic in the UV and only photometric in the optical. Most of our curves were based on spectroscopy in the UV and photometry elsewhere. So we're moving out. We're now learning more about the dust. In fact, we learned a lot more about the dust in the optical, somewhat surprisingly. So then Dirk Massa did an analysis that said, okay, I'm going to look at these wiggles and see what they are. He did PCA analysis, other things. But what we really found out in the end is that what it came down to is the optical extinction is well modeled by a low order polynomial and 3 Drude profiles. And all of these sight lines have the same 3. They have the same center wavelength, the same width. All that varies is the strength. And so these are 3 features that have always been there, but we haven't studied them. First time ever we really say they're there and they're features and they're not just wiggles. What they are, we don't know. They're laboratory. We don't have laboratory measurements to tell us what they are. I think this is a challenge for laboratory work. Awesome. We've come up something new for them to do. Very intriguingly, though, the 2 bluest features at 4370 and 4870, if you add their strengths together and plot that versus the 2175 angstrom bump, it looks kind of correlated. And the highest signal noise ones are in the solid, the less high signal noise ones are in the plus symbols. And so, wow, this is very intriguing that we have this correlation. 2175 we think is carbonaceous. So maybe this is another carbonaceous feature. Awesome. Now we need lab data, lab work to actually understand what these really are. But new features. Okay, now let's move on to the near and mid-infrared. So continuum was usually measured via photometry up until just last year, and I'll talk about 2 papers. But there were features that were measured spectroscopy, and I'll talk a little bit about these before I jump into the new stuff. These were often measured spectroscopically over narrow wavelength ranges, or what I like to say is towards complicated stars that are hard to model or hard to get, hypergiants, things that are not easy to understand and are fairly unique. So it was challenging to get the continuum extinction. And the 3 features that are often measured this way is the ice feature, which I've already talked about. I'll talk a little more about. There's a 3.4 micron hydrocarbon feature and a 10 and 20 micron silicate features. And I'd like to say that the hydrocarbon and the silicate features, these are the two features, the true fingerprints that say we know that interstellar dust has carbonaceous and silicate grains. It's these two features that tell us that. So these are really critical features. So just a little bit about ice, because I don't want to talk about ice. Ice is very complex. And I'm showing that in the upper right plot. As you can see, there's a lot of ice features. You can get water ice, which is that's the top one in the dashed, which gives you that's the bulk of it. But there's also CO2 ice, CO ice, everything mixed together ice. There's lots of interesting ices here. That's awesome. But I'm going to stay simple. And that's looking at that's why we're doing diffuse dust and not dense dust. Dense dust has all these ices, things get complex. But also point out that you need an AV of 3 to see ice. And this is an observational measurement that's shown in the lower right, where they just plotted the column density of ice versus AV. And you can see some of the other kinds of ice also seem to need AV of 3 or higher. So if we stay below AV of 3 in general, we're probably diffuse. And this, just think about it as having to get into a cloud and get shielded from the diffuse radiation field to allow ice to survive. All right, the 3.4 micron feature is one of my favorite features, even though it's incredibly weak. So if you notice here on the left, there's this feature. This is a measurement towards the galactic center. The galactic center has an AV of 30. Wow, I wish I could get a UV spectrum. There's also one to a weaker sightline to SIG OB number 12. It shows this complicated three absorption features. And that's neat. That sounds diagnostic, and it turns out it is incredibly diagnostic. And I encourage you to go look at this paper by Yvonne Pendleton and Lou Alamanola, where all those solid ones, these are laboratory measurements of different kinds of hydrocarbons created different ways. And you can see some of them don't fit and some of them do. That's awesome, because that means we're starting to actually narrow down. We're not just saying it's hydrocarbons. We're saying what kind of hydrocarbon is, what the ratio of aromatic to aliphatic bonds and things like that. So this is a really nice feature, and particularly excited maybe of being able to use JWST to measure this. Although we don't know yet. We think we have the sensitivity. The 10 and 20 micron silicate features. These are the two features just to give you a feel for what they look like. There's some models in there. Right, it's very strong feature. 10 microns is the stronger feature. It's narrower, but still quite broad, a couple of microns wide. And then the 20 micron feature is even broader, right? This is a very large feature. But they're both they're diagnostic of different kinds of silicates, right? Silicates is a broad category of rocks. And you can get a geologist to talk about them, and they see things like pyroxene and olivine and NSATs and all this. So there's lots of possibilities there. So these features are going to help tell us what kinds of these silicates are there. One of the things that's already been shown very clearly is from the laboratory data is that in the diffuse ISM, the amount of crystalline silicates is extremely low. And you can vary. It's a very nice, easy thing to see is on the left. I'm showing you the extinction due to, or the absorption due to amorphous silicates. And you can see the feature can peak anywhere from 9 to 10-ish microns. And then crystalline, now it's not just a peak, it's got a whole bunch of structure. And so you can then model the actual measured silicate feature, and you can see it's pretty much looks like the amorphous. So there's very little crystalline silicates in the ISM. Awesome. We're learning things about the mineralogy now here of dust. All right, so now we're going to go to the near infrared, and we're going to use NASA's infrared telescope facility, which is on Mauna Kea, and if nothing else, it's a great excuse to go to Hawaii and observe, if you can get there. So actually, this is a work that's been done by Marjorie DeClure, another postdoc who's working with me here at the Institute. And this is using this great instrument called SPECS, which is able to take a lot of spectra very quickly. And so we were able to measure, use standard pair method. We're doing the same things. And on the right shows the actual extinction curves that she measured. There's a bunch of them. There's models there that are dotted lines, the dotted red lines. And that's actually just a power law model. And in general, a power law works extremely well. So we kind of knew a power law worked, where we had measurements from photometry that said a power law looked pretty good. But that was from like 5 data points spread throughout from 1 to 5 microns. So now we have lots of spectra. And it turns out, even at spectroscopic resolution, we're seeing it's just a power law. We're not seeing those wiggles that we found in the optical, for example. There is challenges, of course, in doing this from the ground. And that's the middle plot I'm showing. The top there, the atmospheric transition. This is telling you that the atmosphere is not your friend. And in fact, in the extinction curves, you can also see this, there are holes missing. And those are places where the atmosphere is basically opaque and you don't get any flux, right? So you just, there's no measurement there, so you can't do anything. But even outside of those opaque places, in where the windows we can see through the atmosphere are present, notice that there's still a lot of atmospheric lines. And the challenge with this is the atmosphere varies on fairly fast timescales. And so Marjorie did an awesome job. We were able to already show that it's a power law, and the residuals are still quite small. And where we see extra wiggles, maybe we think they're due to the stellar parts. But we're also very excited about getting JWST data. So we'll get to that in the future. So she was able to show, and here's the another rendition showing that the power law is extremely good. This is the average. The power law fits very well. It's a little different than other people's measurements of what the average might be, but sample sizes are small, so that may explain that. One of the things we're able to do in this study is, since these sight lines also have UV, we can look at their average UV extinction curve and see it looks a lot like RV of 3.1. So we know these are diffuse sight lines, whereas some of these other measurements here in Debedau, etc., they're not for diffuse sight lines necessarily. So there may be some variations there due to mixing in of dense material. The other thing that Marjorie did, right, is she actually looked and said, is the 3 micron ice feature present in the diffuse average? I said we didn't want to see it, and we don't see it very strong, but we have a couple of sight lines. In fact, I go back here, you can maybe see in this sight line here, there is ice in we have a couple of dense sight lines in the sample, which we don't use in our average. So we know we can measure ice, but the question was, well, is there ice in the diffuse ISM itself? And there's the measurement she made. It's not a 3 sigma measurement, right? It's very small, and maybe 2.5 sigma. It's not significant, but intriguingly, it's at a level that was predicted prior to this work by Popatov, that said, if ice is present in the shadowed pits of silicate grains, this is the level it would be. And we're about that level. So this is a very intriguing, extremely tentative, not significant at all, but something we definitely want to follow up, because this can have some impact on one of the problems we have in dust is there's more oxygen depleted into dust grains that is in dust grains than we actually can account for with silicates. So this could be a place where we hide oxygen. As I said, intriguing. Another thing to follow up. All right, moving on to the Spitzer Space Telescope. This is work. So now we're going to go from 5 to, we're going to measure the extinction curve from 5 to 30-ish microns, depending on where the sensitivity drops off. Remember, we're looking at stars, so they're dropping like Rayleigh jeans, so lambda to the 4th. They're very strongly varying in the wave as a function of wavelength. So again, we're using mainly sight lines that have UV extinction curves. There's a couple of dense ones in there. You can probably pick out where the dense ones are, even in the UV extinction curve, with their very weak bumps. Don't use those in our diffuse average, but we had them because you couldn't resist. So we had, again, diffuse sight lines. We were able to measure, and you can see the 10 micron silicate feature. And the 20 micron, maybe you can see it. So I'll go to the next page so you can really see it. So here on the left, on the right, on the top, you can see there's the average of most of our sight lines, except those ones with ice. And what we found out is, again, a very simple model works, analytic model. It's a power law plus 2 modified Drudes. And we're using modifieds now because they're more asymmetric. It's one more parameter that allows us to make them asymmetric. So it works pretty well. There's 2 features at 10 and 20 microns. They fit very well. These are definitely, again, there's the average in the UV to show that we're actually measuring something. We're measuring the diffuse mid-infrared extinction now, and we can show that with the UV. And then on the bottom, you can see the residuals. Again, it's pretty smooth, and there's nothing really there. I've indicated the three places where the aromatic emission features are seen. And we don't see them in absorption, at least in our ability to measure them, our sensitivity. So that's interesting, but we don't see them in this diffuse average. Okay, so the other thing, we're able to now do some look at variations and do some direct comparisons we hadn't been able to do before. One is we see strong variation in the S1 is the 10 micron silicate feature strength. In that strength, all right, versus AV, the ratio of that. But we don't see much correlation between the strength of the 10 micron silicate feature and the grain size, or RV, right? RV is our stand-in for grain size. Okay, it's not varying with grain size. I'll mention that. I'll talk a little bit more of that in a second. And for the first time, we can observationally confirm that the 2175 angstrom bump is not due to silicates. Now, we didn't think it was, but we'd never observationally tested it. So we don't see a correlation between 2175 and the silicate feature. That's a confirmation that it's not due to that. And the reason we can do that with this sample is it's the first sample where we've got the measurements in the mid-infrared, where we also have the measurements in the UV. So this is trying to connect things across wavelength ranges. It was one of the goals of this work. Awesome. As I said, maybe it'd been more exciting if they'd been correlated, but then we'd be in a deeper hole of not understanding what's going on. Okay, so last little bit in the Milky Way. So now we've now done spectroscopic measurements from the far UV at from 912 angstroms all the way out to 30 odd microns. Now the question is, can we put it all together, right? They're using different samples. Their RV dependent relationships don't always agree at the boundaries between wavelength regimes. Can we put it together and make a single RV relationship that'll work for all wavelengths, that'll allow us to use this to study dust, and probably more widely usable, people can actually now account for dust at all these wavelengths cleanly with a spectroscopic resolution. So this is, again, straightforward. Now you're just trying to look and how do you make an RV dependent relationship? You basically just fit lines as a function of wavelength, right? You fit a line at every wavelength to A lambda over AV and versus 1 over RV. Now I've done it a little more. I've done it versus 1 over RV minus 1 over 3.1. So my intercept now is the average, the extinction curve at an RV of 3.1. That'll be the A term. And the B term will be how it varies with grain size, or how it varies with RV. And so you do this as a whole bunch of wavelengths, and I've shown here the fact that there's uncertainties on both X and Y, and they're covariant. And we've come up with a more advanced technique to deal with that. And I think for the first time, we're now fully accounting for the covariance and the uncertainties on both X and Y. And so now there's the RV dependent relationship. It's a little different in some places, but it's reasonable. Okay, so now let's look at those coefficients, because now the coefficients that have physical meaning. Beforehand, we didn't always subtract 1 over 3.1. So the intercept was at an RV or 1 over RV of infinity or something, right? Didn't have physical meaning. Now the intercept, that's the average. So that's the extinction at 3.1. Call that the average because 3.1 is kind of the average RV in the Milky Way. So now we can evaluate it, and that's the average extinction curve. It's got the 2175 angstrom bump. It's got silicate features. It actually does have the wiggles, the optical new features. But more intriguingly for me is you can look at the second, the B, the slope thing here. And now you can say, do the features or the continuum depend on grain size? And you can see here that 2175 angstroms depends on grain size because it varies with RV. Great. That makes sense. We think small carbonaceous grains are there. So if you have fewer small grains, you're going to have, fewer small grains means higher RVs. All right, your bump will be weaker. Okay, that makes sense. You can actually see these optical features are there, right? They actually do wiggle at the right wavelengths, and I have blow-ups of this. Right, these new optical features are likely due to small grains, both because they vary with RV and because they correlate with 2175. But notice the silicate features don't vary with RV, right? We already saw that in the study that focused on that, but that really confirms that we don't, the silicate features, they don't depend on it. That's okay, because in fact, we think there are silicate grains of all sizes, and they all contribute to the silicate features. So that makes sense. You're not going to really see a huge size difference if all your grains contribute to the feature, not just small grains. Oh, Ida, go for it.
Yes. So I have a question about the hydrocarbon feature. So I think you've mentioned that the hydrocarbon features are weak compared to the silicate features. So yeah, that's the slide there is the one shows the relative strength between the two. Are there is it weak just due to the nature of these hydrocarbon features, or does it hint the composition of dust between the ratio between silicon grains and hydrocarbon dust?
So it is intrinsically weak, i.e. that the hydrocarbons you measure in the lab, it's just weak.
Okay.
So I think if I remember correctly, right, they've since you measure it in the lab, you know what it is, you know how many carbon atoms it takes. And so probably 20% of the carbon at least is locked up in this grain material, not all of the carbon. And so asking that question, right, how much does this constrain how much carbonaceous material we have versus silicate? That's what we're getting to. That's what we want to get to. I will say that Marjorie looked for this feature in her sight lines, but we didn't have the sensitivity from the ground to actually measure it. So the goal is to do this with JWST. And so, yes, we're going to try to do this for exactly that region. It's diagnostic. And then we can say, something I would love to do that we have not done is, can we correlate this feature with 2175? We haven't been able to make that measurement yet. But that's the plan. We'll get there. But it's a good question. Yeah. All right. So we're through the Milky Way. So a quick summary of the Milky Way. I know I'm running out of time. Sorry about that. Spectroscopic from the far UV to the mid-infrared. Everything is smooth. In the far UV, it peaks at 800. That's good. The H2 correlates with the far UV rise. They're co-spatial, this grain with molecular. That's intriguing. We really need to spend more time thinking about that. There are new optical features. Their origin really is unknown, but at least we think they're probably small grains. The near infrared is definitely a power law. It might include water ice, which is intriguing from the oxygen abundance problem. Mid-IR versus UV features. Yay, 2175 is not due to silicates. We don't have to rethink our dust grain models. And now we have this RV-dependent relationship that's it should say one, not on relationship, one relationship for all wavelengths. Okay, I'm going to fairly quickly go through the beyond the Milky Way so we can get to the future. So we've known for a long time, this is back to IUEA days, that in the Magellanic clouds, things don't always look like the Milky Way. And on the right, you can kind of see they kind of look normalish, but maybe a little steep. And on the left, they're much steeper. Those left ones are kind of in that red circle in the Magellanic clouds. That's near 30 Doradus. You do a little more work, and you can find out that, in fact, it's not really sorting by distance to 30 Doradus, because 30 Doradus is like any star-forming region. It's eating into a molecular cloud. And so the material in the molecular cloud is much more normalish. So it's really, most of the LMC looks like the Milky Way, except for this region near the LMC2 supershell, which has weaker bumps and kind of a steeper extinction. And that segues into the small Magellanic cloud, right, which has, again, been known from the 80s to have very steep extinction and effectively no bump. I don't have the plot. I should put it in the white space there. But although there was one sight line that showed a bump. So they've even known from the 80s that there was one sight line in the SMC that had a 2175 extra bump. So here's where I've done a little contribution. Here's the total number of sight lines that we currently have that have good extinction curves throughout the UV in the SMC. Yes, there's only 5. And we had to go to Hubble to get one more. The 4 that don't have a bump, right, they're all in the SMC bar. And spread throughout the whole SMC bar. That's a large region. The one with a bump is in the wing. Is that significant? Actually, probably not. I'm going to skip that because we actually are expanding the sample with the UV extinction curves using Hubble. So the long-running program that I'm the reason it hasn't been published, and I'm working hard on it. I swear soon it'll get published. And we do know that there is a couple of bump sight lines we've confirmed in the smidge region of the SMC. This is this region that's studied in the lower star-forming bar. So that is extremely intriguing. And we still don't fully understand why, but that correlation between the far UV rise and molecular hydrogen might be telling us something about that. It might be molecular material we need, but that's tentative, and we'll get back to that. We are doing work in M31 and M33. This is a preliminary work we did with Hubble in showing the first really clean UV extinction curves in M31. They kind of look Milky Way, maybe a little LMC-like. So Milky Way is in red, and LMC2 is in that green, and then the blue is the SMC. So they definitely don't look like the SMC. That's okay. M31 is more solar metallicity. We're now got an expanded program where we have more sight lines in M31, and we have the first sight lines we're measuring in M33. They all have, we all have HST photometry, which is awesome because these are more distant galaxies. In general, they look similar to the Milky Way, maybe LMC2-ish. And we're looking to study radial and metallicity variations in M31 and make the first measurements in M33. And there's a couple of papers in prep. This is work that I'm doing with Petya Yanachilova America Jones, another postdoc here at Space Telescope. And so kind of quick summary there, right? The Large Magnetic Cloud, it's a half solar. Now I'm putting the metallicities in to make things more interesting, right? Most of the LMC is similar to the Milky Way, but we see differences in this LMC2 supershell region, which is near 30 Dor. So maybe nearby star formation is important. In the Small Magellanic Cloud, now we're down to 1/5 solar metallicity. Most are very different from the Milky Way. They're very steep. They have no bump. We know that even from our expanded sample. There's a small fraction, maybe 10%, maybe 5% that are closer to the Milky Way. They're much flatter, they're more gray, and they have a bump. And M31 and M33 at this point look similar to Milky Way, but that's a very preliminary analysis. We're still working on that. All right, then a quick run through the future. We always like the future, right? The answer here is more of everything, but in more specific, we definitely want to do more galaxies with HST, and we're put in proposals. We're not always successful, but we know to put them in again. So we'll continue to put our proposals in. In particular interest for me is I would like us to investigate more low metallicity galaxies in the local group. We kind of can do this in the local group, kind of hard to do outside of that. And really here I'm focusing on UV because that's where the diagnostic features are that we can get to. So is the SMC unique or not? Is it due to the low metallicity, or is it due to the fact the SMC is being ripped apart by the LMC, literally, right? And so maybe there's extra processing there. And we want to expand our samples in the larger galaxies. For example, does the M31 RV-dependent extinction relationship work in, say, M31 or M33? That's what would be nice to know. And even in our Milky Way, we really will need to probe more high and low RV sightlines, i.e. more sightlines with much higher than average grain size and much lower than average grain size to really understand what's going on there. It's likely we should see curvatures in this RV relationship and all that. So that would be exciting. Now, what about JWST? Unlike HST, where we don't have anything new that's going to come, JWST has 2 Cycle 1 programs that are PI'd by Marjorie DeClerc, the postdoc working with me, and Sasha Zegers. And these are, in the end, we'll get 21 Milky Way sightlines from 2.4 to 28 microns. And this is where we really think we have a shot at measuring not just the continuum and the 10 and 20 micron silicate features, which are quite strong, but the 3.4 micron hydrocarbon feature, which is very weak. But JWST should have the sensitivity to allow us to do this. And so now, and these, at least, and we do have a Hubble program for Sasha's that is going to get us the UV and optical spectroscopy from Hubble in order to get that part of the extinction curves, and they already exist for Marjorie's. So we'll be able to do this comparison between the UV optical and near and mid-infrared again, which I think is very diagnostic of what the materials are. We also want to map features photometric, and I'll show one slide on that. I'd like to look and see how about the LMC and SMC, the continuum and silicate measurements in the mid-infrared are. And of course, other galaxies would always be awesome. And just a little bit on this photometric measurements, the idea here is to use bands from JWST. JWST has many more bands than we had with Spitzer, or even anything really. And so we have enough bands now that now we can have a band that's, say, at the silicate feature, we can have one on either side and one in the middle. And you can imagine how then you can fairly straightforwardly measure the strength of the silicate feature. And the same can be true for the ice and the hydrocarbon, the 3.4 micron hydrocarbon feature. So now we can now map these features much, much more efficiently, i.e. make maps of clouds and regions, as well as have targets for follow-up near and mid-infrared spectroscopy. And I'm going to leave you my summary, and that's it. Thank you very much. Any other questions?
Thank you, Karl. There's a question from Sheng Yuan. Sheng Yuan, please go ahead.
Hi, thanks very much for the great talk. Just a couple of basic questions. The first one is you at the beginning you mentioned about the extinction and the attenuation. So for Magellanic Cloud and beyond, when you do these observations, are you able to measure just the extinction, or you are starting to get in the attenuation part?
No, go ahead. Yeah, sorry.
Yeah. The other quick question is, I may have missed whether you have all these results have provided new insights about the size distribution.
Okay, so I'll answer the first one and then the second one. So we think that at least definitely in the Magellanic Clouds, things are well resolved enough that we can, individual stars, we're able to measure extinction. And we have good reason to believe that's in M31 and M33. We can do that as well. How much further we can go, and even how worried we should be in even M31, M33, we don't know yet. Although I'm going to actually, regress back to my grad student years and do dust radiative transfer models and test that. So we can do the radiative transfer models when it's very complex, like the lower thing here, the lower graphic. But we can also do the ones even for the upper graphic, right, where it's a star with dust in front of it. And I slightly lied to you, and I said it was just scattering out of the beam. There's a little bit of scattering into the beam as well. Any size beam is going to get something, but it's so small that we ignore it. So obviously, at some point, as we go to more and more distant galaxies, we're going to not be able to ignore it. So I think the answer is I think we're fine, but I would like to actually quantify that statement, because also I want to answer the question: how much further can we go with a given telescope? Right? How far can Hubble go? How far can JWST go? Because it's really a question of how well can you resolve the galaxy, right? And your beam is small enough. And so I think we can quantitatively just show that, and I'm hoping to do that in the next few months. But I went on vacation and thought about it and decided I wanted to do the project. So that's the problem. Don't go on vacation. You'll come up with new projects. And your second question, I'm sorry. How well? So we've made these measurements. A lot of the measurements have just come over the last couple of years. And so I think their dust grain models are starting to use it. As I just said, that Bruce Drain and Brandon Hensley have used it, or at least compared to it in their new Astro Dust model. I don't know how much they used it as a constraint versus just seeing whether they were consistent with it. I can say that I did check that in my 2021 paper, and in general, all the dust grain models were a little low or a little high, but didn't actually hit the mid-infrared extinction curves, for example. So I think using the new stuff, it takes a little while to get into the dust grain modeling. Hopefully soon, or maybe one of us will have to start doing dust grain modeling to get it in. But yeah, that's definitely what we want to do.
Thank you so much.
No worries.
Hiro, please go ahead.
Interesting talk. Thank you very much. And so M33 and SMC have similar metallicities, but extinction curves are very different. Do you have any interpretation about?
I wouldn't say yet. I don't think we know yet if the LMC versus M31 are different. We're just getting to work on the M33 extinction curves. So I don't. To first brush, they look similar. Right? So the LMC, remember, most of the LMC looks like the Milky Way. It's only near that big 30 Doradus, and so maybe near one of the very massive star-forming regions in M33, and I think there's one. Maybe we'll see some of that evolution in the extinction curve, but I can't answer that question yet. I'm very excited about for exactly what you just asked. Right, they're the same metallicity, but they definitely have a different interaction history. Right, M33 is much more quiescent than the LMC. Right, the LMC is much more even because it's got the SMC nearby running around. So I don't know.
Yeah. Okay. Another question is, you mentioned variation of silicate features at a certain point, if I remember correctly. But in the end, maybe silicate features are more or less constant. I'm a little confused. Well,
No. So here, yeah, good question. Good question. So here's, say, either this plot here on the left or the one in the middle. This shows the silicate strength divided by AV, and you can see it varies by a factor of 2.
okay.
But definitely, it clearly varies, but it doesn't vary with RV. So when then I made this plot, right, I said, okay, does it vary with RV? And the answer is no. And I think in the lower corner here, this is 10 microns. I mean, maybe there's a little slope, but when I look, do I believe that fit now that I can, I'm visualizing it here, this middle bottom plot. I'm not sure, I'm small number statistics. So I don't think, so clearly the strength of the silicate feature doesn't vary with RV. It varies with something, but not grain size.
Okay, I see.
That's all we can say. So.
Okay, yeah.
Yeah.
Thank you.
Awesome.
Any questions from the audience? I have a question, although I feel like I should know the answer to this one. So,
Okay.
do you know if anyone has tried to compare the strength of the 2175 micron bump to the Q part derived from emissions, and trying to use that to explain why we don't see the bump in SMC?
That's that is a very good question, and in fact, we picked this sample in the SMC, right? All these sight lines, right? One of the criteria we did in picking them was that they had a range of Q pause based on Karen Sandstrom's work, and unfortunately, it doesn't seem to matter.
Okay.
Right. So we basically, most of these sight lines don't have a strong bump. You can actually see in this plot there's a little bumps, and that has to do with we're using a slightly different technique. So the foreground is included in these extinction curves, and we need to deal with that. So a little bump could be Milky Way, and likely is. So once we deal with that, but it just doesn't look like there is. I mean, we had a range of Q pause, and the bump doesn't seem to correlate with it. Now, there are reasons why you might, okay, Q pause measure in the infrared, and it's a total column through the whole galaxy over some wider beam, where these measurements are pencil beam, right, to just the star. So maybe that explains it, but I don't think it fully explains it. I think it does call into, we have in some dust grain models, it's assumed the 2175 angstrom bump and the aromatic PA emission features are from the same grains. That's an assumption at this point. That we need, from my point of view, right, we should test that. And that's one of the reasons we did this study. I will tell you that one of the reasons this paper hasn't been published is it's not a very exciting result. We've confirmed everything, and there's no good correlations.
Okay.
It has to be written. I have to write the paper because it's important. Right?
Yeah, it's important. It's not important.
But it's you do the exciting results first, right?
Right.
So, yep.
Hey, thanks. Any more questions from the audience? Yuhua? Are you?
She showed up.
Yeah. Yuhua, do you have a question?
Okay. Yeah. Hey, Karl, I want to tell you that I really enjoy your talk. It's an excellent talk. Fantastic. I never say this to any speaker. You're the first one.
You're too kind.
I really enjoy it. I didn't fall asleep at all. Okay.
Thank you very much.
Okay, so if there's no more questions, then let's thank Karl for participating with the 12-hour time difference.
No worries.
Hey,
Awesome.
Thank you.
All right.
Yeah, so I think that's the end of our colloquium today.
Okay. If anyone has more dust questions, feel free to contact me. I always like talking about dust. Okay.
Okay.
Thank you. Thanks, Ida. Thanks, everyone.
Thanks very
Bye.
much.
Very